Turns out it takes energy to change the state of a substance as well as to actually raise the temperature of a substance. We refer to this as specific latent heat. So it's got a nice easy equation, Q equals ml. Q is still quantity of heat, m is still the mass of the substance, but L is this specific latent heat. And again, when you see this word specific, you kind of think in your mind like it's specific to any given substance. So any given substance has a specific latent heat. Water has a number, and some different metals, whatever, all these things have a certain number. And again, you can look up this value for whatever substance we're talking about. Turns out there's two specific latent heats, though, two different types, because there's different substance changes or state changes, I guess, for a substance. So fusion is if we're going from solid to liquid or vice versa. So if you're freezing or thawing something, there is a specific latent heat of fusion, and you'll see it as like LF. Okay, this thing here is an L. So LF, that's if you're involving a solid. Whereas vaporization, like the word sounds like, it involves gas. So if you're going from a liquid to gas, there is the specific latent heat of vaporization. Okay, so we got to remember that. Let's try this one out. What mass of water can be changed into vapor by adding this quantity of heat energy? Anytime you see something in joules in this section anyways, that is quantity of heat energy. We're looking for a mass. We've got to look up, like in our textbook or online somewhere, we have to look up our latent heat value, our specific latent heat. The question is, which one do we want? Well, in this case, we want the one that involves vapor. Okay, so that is our specific latent heat of vaporization. And the number is, if you look it up, it's 2,255,000. That's a big number. So there's a lot of number there. Anyways, yeah, we just kind of know that, yep, it's a big number. And I was going to figure out the units. Q equals ml. Don't have the number in front of me, so L would be joules per kilogram. Do be careful. In your textbook, I think this number is written as, let's see, LV. Sometimes, I think in your textbook it's written as 2255 kilojoules. This is the J per kilogram. Okay, so just watch this. If it's in kilojoules, we want to convert it to joules per kilogram. I think that's how it's written in your textbook. Okay, so just be careful of that if you see that. Our equation then, Q equals ml. We know this number. We know this number. We're going to divide them. And what do we get? 3.3 times 10 to the negative 3 kilograms. So mass, that's about 3.3 grams. And I suppose for sig digs, this is a weird question where we've got way more sig digs in the question. I suppose you could say 3.3000 grams if you really wanted your correct number of sig digs. Okay, so nothing too hard there, but where does it get a little bit harder? Yeah, there we go, 3.3 grams. Where does it get a little bit harder? Here's the type of question where it gets a little bit harder. Okay, so we're kind of putting together a couple different things here. What total energy is needed to raise 2 kilograms of water from 50 to 120 degrees Celsius? And remember, water boils at 100, so here the water must have already become steam. Okay, so what we're doing is, I want you to imagine kind of like a thermometer or something. We're kind of raising the water from 50 degrees Celsius all the way up to 120 degrees Celsius. But remember, something happens right here. And that something is liquid water becomes steam. Okay, so what that means is we're going to have to raise the temperature of a substance. We're going to use this equation, Q equals mc delta T. Let's call it Q1. Here we're also raising the temperature of a substance, but it's actually a different substance. So down here it's water, that we're raising. Up here it is steam that we're raising the temperature of, which means right here we're actually going to change the state from water to steam, which means we are going to have to use Q equals ml. Okay, so I'm just going to label them Q1, Q2, Q3. We're going to actually find 3 different Qs, and then we're going to add them all together. So this is a bit of a long question. So let's say sort of step 1. We are raising the temperature of our water from 50 degrees Celsius to 100 degrees Celsius. Okay, so that's kind of our step 1. We're going to use this, Q equals mc delta T. This is Q1 that I'm talking about in my labeling scheme. The mass of water is 2 kilograms. C value for water, 4,200. You're probably already memorizing that one. The temperature change, remember T2 minus T1, 100 minus 50, that's just giving us 50. Q1, 420,000 joules. Okay, I'm going to stick a little box around here. This is not our final answer. This is Q1. Step 2 then is we have to convert water to steam. Right, this is our change of state. That means we're using this thing, Q equals ml. And just remember, we're using vaporization because it's involving vapor, steam. The mass is still 2 kilograms. Okay, so imagine that we're able to capture all the steam. We're not losing any steam to, I don't know, the environment. Q2 then, 4,510,000 joules. That's a big number. Step 3, we're still not done. Step 3 is this one up here. We have to raise the temperature of the steam from 100 degrees Celsius up to 120. Okay, so step 3, if you're raising the temperature of a substance, we're back to this equation, Q equals mc delta T. This is Q3. We still have 2 kilograms. The C value for steam is 2,000. And the temperature change, remember it's T2 minus T1, so 120, take away 100, just 20. We multiply all that stuff, we get 80,000 joules. Again, not our final answer, just a number that we're going to need. And then in order to find out our total is Q1 plus Q2 plus Q3. We're just going to add all those values together. So 420,000 plus 4,510,000 plus 80,000. And we're going to get a total energy of, let's see, 5010, lots of zeros, joules. Q total, that's approximately, so 5.01 times 10 to the 6 joules. That's like 5 million joules of energy. It's a lot. And just notice how much of it is right here. Okay, so raising the temperature of water, we went 50 degrees. That's a pretty big change in this first part up here. That's a pretty big number too, but 400,000 compared with like 4 million. It's 10 times as much just to convert it to steam. That's a big amount of energy in there converting it to steam. Anyways, total energy. The dreaded question is, what if I started off at ice and went all the way to steam? You would have to go from like raising the temperature of ice, converting it to liquid, raising the temperature of water, converting it to steam, and then raising the temperature of the steam. You'd have to do 5 steps. I don't know if I'll give you that, but who knows, maybe.